let's talk about some special probability functions, which there are specifically 3 of that we deal with in this class. Probably the most important, they're all probably, the one of them is less important, but this one and another one are probably the 2 most important of the 3. So this one is kind of introduced via this problem. The lifetime t in years of a battery is an exponential probability density function. F of t is equal to 1/3 e to the negative 1/3 t on the interval from 0 to infinity, where t is measured in years. So potentially, right, a battery could last a really long time, right? There's no kind of upper limit on how long a battery could last. Obviously, it's not going to last forever, but it could last a really long time. So that's why it's from 0 to infinity. And so our exponential probability density function looks like this. It has a y-intercept of 1/3. So if you set this is t equal to 0, you're going to get 1/3 times e to the 0, which is 1/3 times 1. And I just thought it was worth pointing out that that means that this integral from 0 to infinity of 1/3 e to the negative 1/3 t dt should equal 1. Because again, the area under a probability density function should always equal 1. That's kind of one of the things that has to be true. The other thing that has to be true is the function has to be non-negative, right? The function always has to be above your horizontal axis. Or it could touch it, I guess, but that's kind of weird. And so we want to ask some questions. We actually just want to point out that this integral is 1. So the way you would show this integral is 1. And so the exponential probability density function is kind of a pain in that it is an improper integral if you're dealing with any of it a lot of the time. So we should all believe it's 1 because it is a probability density function. But here's the work. The integral from 0 to infinity of 1/3 e to the negative 1/3 t dt, we would rewrite it as a limit. The limit is b goes to infinity from 0 to b of the same function of the, and then we would integrate this. The integral of 1/3 e to the negative 1/3 t is just negative e to the negative 1/3 t. Right? If we take the derivative of this, the derivative of this is negative e to the negative 1/3 t times the derivative of that, which is a negative 1/3, which gives us a positive 1/3 e to the negative 1/3 t. Then I like to rewrite it. When I have negative powers, I usually like to make them positive by bringing them down to the denominator. So I'm going to write this as negative 1 over e to the 1/3 t. The limit of that is b goes to infinity from 0 to b. We plug in the b, we plug in the 0, and negative 1 over e to the 1/3 b as b goes to infinity. This denominator is going to get infinitely large, so this fraction is going to get infinitesimally small. So we get 0 minus 1, which ends up being 1, which we already knew it was supposed to be, but it's still good to see the work. So then we can ask questions. Let me move things around a little bit here. And definitely, this distribution is definitely showing up on both of your homework assignments. Yeah. Problem 4 on Lee's last homework assignment, and it's showing up in problem 3, part 3 in Ma's last homework assignment. So this one definitely is showing up for everyone. So let's see. So we can ask some questions. Like, I think I'm going to erase. No, I want to find what's the probability that the what's the probability that the battery lasts less than 2 years? Okay, so all I'm really trying to do is find, like, let's say 2 is like about there. All I'm trying to find is the probability that the time is between 0 and 2. So I'm trying to find the area under the curve when t is between 0 and 2. Well, we know how to do that, right? We know how to integrate. So, like we've already done the integral. Let's do it right up here. So that probability that the battery lasts less than or equal to 2 years is going to be and I want to, so probably the time it lasts is less than or equal to 2 and bigger than or equal to 0, but we know we have to start 0. Is going to be equal to the integral. And I don't know if you're choosing to talk about this is pretty typical notation. Right? You're trying to find the probability the time it lasts is between 0 and 2. That's going to be the integral from 0 to 2 of your PDF, which again is 1/3 e to the negative 1/3 t. Good news, we already know how to anti-differentiate that function. Right? I did it on the other side of the board already. So that's going to equal, let's see. So I don't have to use anything improper here because my limits of integration don't have any infinities in them. And this function 1/3 e to the negative 1/3 t is defined everywhere. So that's going to be just the integral of this, which is negative e to the negative 1/3 t, evaluated from 0 to 2. Well, that's not terrible. That's just going to be negative e to the negative 1/3 times 2, so negative 2/3, minus negative e to the negative 1/3 times 0, which is going to be negative e to the negative 2/3 plus 1, or 1 minus e to the negative 2/3, which is approximately 0.487. So there's a 0.487 probability, or a 48.7% probability, or percent chance that the battery will last less than 2 years. Okay. So then, to a different color here. Okay. What's the probability that the battery lasts more than 2 years? Everybody should be able to tell me what this is going to be. So we're finding this. Let me ask you guys, what should the black part and the red part add up to? Or another way of asking this, how much area is under this curve? Yes, Madison, and to the other person who said the thing, you've jumped straight to kind of what the answer is going to be to the actual question. But yeah, so the total area under this curve is exactly 1. So if I want to find this red part, I'm going to do 1 minus the black part. But the black part is this thing we already calculated. So yeah, we're going to get 1 minus e to the negative 2/3, which is going to be just positive e to the negative 2/3, which is going to be approximately 0.513. But just as a kind of a point of interest here, right? If they're asking for the answer, this is the answer you want to give. Or here, this is the answer you want to give, right? Those are the exact answers. And these other things are the decimal approximations, which are not exact, but give us a good idea, right? Because I don't know what e to the negative 2/3 really is close to, which is why we use a calculator. Be like, oh, okay, it's about that much. Yeah. So again, right, if you know how to basically, if someone asks, and for words are challenging. So the reason I point this out is because you could have done this the more challenging way, right? You could have done this as the integral from 2 to infinity of 1/3 e to the negative t over 3 dt. But if I can avoid it, I am going to avoid doing an improper integral. So for example, if we asked a different question, like if someone said, hey, James, what's the probability that the time that the battery lasts is more than, say, 4 years? I still wouldn't do this integral. I would do 1 minus the probability that the battery lasts less than or equal to 4 years. And that's going to be 1 minus the integral from 0 to 4 of 1/3 e to the negative t over 3 dt. So for these exponential probability density functions, if they're asking you the probability that like the time is more than some number, it is usually more convenient to find the probability that the time is less than that number and then subtract it from 1 to get the answer you're looking for. It's usually a more simple calculation to do. Let's ask some other questions. So I would like to find the median battery life. So you remember the median of a thing is the number that splits it exactly in half. So we're trying to find the battery life where this side here is 1/2 and this side here is 1/2. So you could either do one of two integrals, and I bet you can guess which one I'm going to pick. You can either say, okay, the integral from 0 to m of my PDF needs to equal 1/2, or you can do the integral from m to infinity of 1/3 e to the negative 1/3 t dt equal to 1/2. Which one do you think I'm going to pick? The one that's improper or the one that's proper? The one that's proper. Yeah, of course, right? Typically, if we have a choice, we try to, not that improper integrals are terrible, they're more work to deal with. So we usually try to avoid them if possible. Sometimes it's not possible. Sometimes you have, like if someone had said, show this as a PDF by showing the integral is equal to 1, you're stuck. You have to do the whole improper integral. So let's do this one. So again, I'm going to do this integral, which we already know how to anti-differentiate this. Again, right, the way, and I didn't actually say it's super kind of good. The way I anti-differentiated this, I said, oh, the integral of 1/3 e to the negative 1/3 t is 1/3 e to the negative 1/3 t, and then I'm going to divide by the coefficient of t, which is negative 1/3. And the 1/3 divided by the negative 1/3 gives you the negative 1. This is going to be negative e to the negative 1/3 t from 0 to m equal to 1/2. And I really should write an equal sign here. I'm getting a new equation. And so then I'm going to plug them in with the integration. I'm going to get negative e to the negative 1/3 m minus negative e to the 0. And that's supposed to equal 1/2. So I have negative e to the, I'm going to write that as negative m over 3 plus 1 equals 1/2. Subtract 1 from both sides. Negative e to the negative m over 3 equals negative 1/2. Multiply both sides by, oh, sorry, there's some. With problems finding medians, will the constant always cancel out to just one when doing the integral? That's what I've noticed. When you say the constant, I'm assuming you mean like the second part of the, like this part right here. Is that what you're talking about? No, like in the first part without. Oh. So it depends. But what I will say is specifically for exponential probability density functions, where it's something times e to the something times t, they actually have a very, very specific format. And yes, when you integrate them, that constant always ends up canceling and leaving you with a negative 1. And we'll definitely, once we finish like going through this whole problem, we'll talk about how for exponential probability density functions, there's actually kind of a very easy way to deal with all of them. They all have the same general format, and there's like a real short answer to what's the answer to kind of the mean, the median, the variance, all that kind of stuff, standard deviation. So yes, yeah, no, not at all. It's a good question. So multiply both sides by negative 1 take the natural log of both sides. So yeah, sure, natural log of both sides. So you get negative m over 3 equal to the natural log of 1/2. Multiply both sides by -1 again. You get m over 3 equal to the negative natural log of 1/2. And I do want to point out that the negative natural log of 1/2 is just equal to the natural log of 2. Right? You can bring that -1 up as a power, and then 1/2 to the -1 is 2. So then finally, the median is going to be 3 times the natural log of 2, which is approximately 2.07 years. Which again makes sense if you think about the first problem, right? The first problem, or maybe not the first one, but probably the time was between 0 and 2 years was about 0.487, which is pretty close to a half. So it's not surprising the median is just a little bit more than 2. Cool. Okay, let's talk about the expected value. And this is where we're going to take a detour. So, yeah. So let's find the expected value. So the expected, when someone says the word expected, you should think average, mean. The expected battery life. So to find the expected value of a probability density function, if the expected value is the integral of x times your probability density function, which in this case is going to be the integral from 0 to infinity, right? It's over the whole interval of x times 1/3 e to the -1/3 x dx. And here we are going to need, except we're using t's and not x's. I mean, it's not a big deal, but it's good to be consistent. Okay. Now the issue here is that, well, it's not an issue so much as that we have to use integration by parts. So I'm going to let u equal t and dv be the rest. And the reason one of the reasons I'm including that 1/3 there is because we already know how to integrate this, right? We've integrated this like 3 times already. So the du is going to be 1 dt. And the v is going to be the antiderivative of this, which we already know is negative e to the -1/3 t. So now, this integral, I always feel like I put this in the wrong place. This integral is going to be equal to uv, which is a negative t e to the -1/3 t, minus the integral. And so not that I did this wrong, but I should be a little bit more careful. I should really be writing this as let me back up a tiny bit. Let's just do the antiderivative first, meaning I'm going to totally ignore the limits of integration, and I'm just going to say that the integral, the indefinite integral of t times 1/3 e to the -3 t, sorry, -1/3 t is equal to this times this, so negative t e to the -1/3 t minus the integral of v d, which is negative e to the -1/3 t dt. Minus is a plus. So then we get negative t e to the -1/3 t plus e to the -1/3 t divided by -1/3. So the integral here is negative t e to the -1/3 t minus 3 e to the -1/3 t. Okay. So then we need to do all the limit stuff as well. So I'm going to erase this part here because I don't think we need it anymore. We've got this. So we can say that our integral here, that's going to be the limit as b goes to infinity of the integral from 0 to b of t times 1/3 e to the negative 1/3 t dt. And then that's going to be equal to the limit as b goes to infinity of the integral of this, which we just found out was all this. So I'm going to rewrite this just slightly. I'm going to write this as, so things have positive powers. I'm going to write that as negative t over e to the positive 1/3 t. And this is going to be minus 3 over e to the 1/3 t from 0 to b. Okay, stop me if you have questions, or interject, or type something in the chat. So then we're going to plug in our limits of integration. So we get the limit as b goes to infinity of negative b over e to the 1/3 b minus 3 over e to the 1/3 b minus 0 over e to the 0 minus 3 over e to the 0. Okay, so we're going to say what the answer is, but then we're going to talk more about it. So clearly this part is going to 0. Maybe not clearly, but if we talk about it a little bit, it'll be clear. B is infinitely large. E to the 1/3 times b is also infinitely large. So this fraction is infinitesimally small because you're dividing by something that's infinitely large. This piece here, that's the piece that we're going to have to talk about more. So that piece does require a L'Hopital's rule. What we can say now, which is a little hand wavy, but it's good enough for the moment, we're going to talk about L'Hopital's rule right after this, is that, well, the numerator is going to negative, let's actually put the negative out in front, so we don't have to worry about that. It's not a big deal, but the numerator is going to infinity. The denominator is also growing to infinity. But the denominator is growing to infinity at a much faster rate than the numerator is. Like when b is 1,000, the numerator is 1,000, and e to the 1/3 times 1,000, and let's see, 1,000 divided by 3, e to the 333rd power is about too big for the calculator. So, right, 1,000 over a number too big for the calculator is probably pretty small. So this is also going to 0. And again, we'll say more about that in just a minute, I promise. But our answer here ends up being 0 minus 0 minus 9, so plus 3. And it will tell you it's not a coincidence that we got 3. And the coefficient that we started off with was 1/3. Let's actually, I want to finish this problem because there's a couple more things I want to say about it, and then we'll talk about these things in general, and then we'll talk about L'Hopital's rule. So let's talk about the variance and the standard deviation, and then we'll make some statements about exponential probability density functions in general. So the variance, oh, yeah, that's actually going to be yeah, okay. So the variance is kind of we should back it. We should talk about L'Hopital's rule. So let's take a quick journey to L'Hopital's rule, man. So L'Hopital's rule. Here's what L'Hopital's rule says. L'Hopital's rule says, I have a different pen over here. Oh, there we go. There we go. All right, 1 second. So let me go over here. So here's what L'Hopital's rule says. And so L'Hopital's rule, I should point out, is only to deal with limits. So if you have a limit as x approaches a, A can be a real number, or A can be infinity or negative infinity, of some quotient, f of x over g of x. And if that limit is either an infinity over infinity type, like the one we were just doing, or also a 0 over 0 type, these are both called indeterminate forms, then it is true the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. That is L'Hopital's rule. That if you have one of these two indeterminate forms for a limit, that you can take the derivative of the top and the derivative of the bottom and take the limit of that, and it'll give you the right answer. Kind of neat. So let's look at a few examples, and then we'll go back to what we're doing. And honestly, I imagine they mostly, if your teacher's talking about it, they mostly intend it probably for these types of problems we're doing with the improper interval. So that's probably where it's coming from this class. Let's look at an example. So the limit as x goes to infinity of x squared over e to the x. Well, this is clearly an infinity over infinity type of limit. As x goes to infinity, x squared gets infinitely large. As e to the x goes to infinity, e to the x gets infinitely large. So we can use L'Hopital's rule. Often when we use L'Hopital's rule, if people are using it, they write an L apostrophe H above their equal signs to let the person grading it know they're using L'Hopital's rule. So then we still have a limit. So it's always, when using L'Hopital's rule, it's always going to equal the limit. And now we're going to do the derivative of the top, which is 2x, and the derivative of the bottom, which is e to the x. All right, we're not using the quotient rule here. It's literally just the derivative of the top part over the derivative of the bottom part. So then, as x goes to infinity, 2x is still going to infinity. And as x goes to infinity, e to the x is still going to infinity. So just like this was an infinity over infinity type, this is also an infinity over infinity type. So we use L'Hopital's rule again. So we get the limit as x goes to infinity of derivative of 2x is 2. The derivative of e to the x is still e to the x. Now we don't have an infinity over infinity type anymore. We have 2 on top, which is a constant, over something infinitely large on the bottom. And the constant divided by infinity is going to be infinitesimally small. So we get 0, which is a much more rigorous way of showing this limit to 0, as opposed to saying, well, e to the x gets bigger faster than x squared, so the denominator is bigger, so the fraction goes to 0. It's also not invalid, it's just less kind of formal. Let's look at a couple more examples just to kind of make sure everyone's cool with this, and then we will go back to our regularly scheduled program. So, a couple other examples here. What about the limit as x goes to infinity? Here's one you should know without using L'Hopital's rule. Not that you can't use L'Hopital's rule, but just you should already know the answer. So the limit is x goes to infinity of 6x squared plus 5x plus 4 over 3x squared plus 2x plus 1. Everybody should be able to type in the chat what this limit is supposed to equal. It is something we definitely talked about in 16a, where the degree, if the degree on the top and the degree on the bottom are the same, the limit should equal exactly. Thank you, person in the direct message. That's correct. Anybody else want to tell me what it is? Yeah, good, awesome. Right, it's exactly 6 over 3, which is 2. And you can either, there's like, so the shortcut is, right, if the degrees are the same, it's just the quotient there. You could also do the thing, and that's really the shortcut for dividing everything by the top, the highest power of x in the denominator. So you could do it the old way and say, oh yeah, that's the limit as x goes to infinity, divide everything by x squared. So you get 6x squared over x squared plus 5x over x squared plus 4 over x squared divided by 3x squared over x squared plus 2x over x squared plus 1 over x squared. And then that's just going to be 6 plus 5 over x plus 4 over x squared over 3 plus 2 over x plus 1 over x squared. And all these things divided by x or some power of x, those go to 0. So you get 6 over 3, which is 2. But we could also use L'Hopital's rule. It's an infinity over infinity type. So we could say this is equal to the limit as x goes to infinity. And let me write a little L apostrophe H of the derivative of the top, which is 12x plus 5 over the derivative of the bottom, which is 6x plus 2. And then still infinity over infinity. So we do it again. We get the limit, still a limit, right? It's always a limit. It's x goes to infinity of the derivative of the top is 12. The derivative of the bottom is 6. 12 over 6 is 2, and the limit of a constant is just the constant. So look, same answer. Sure thing. Yeah, we can definitely do that. I was definitely going to talk about that. Let's do one or two. Yeah, let's do one more infinity over infinity one. So I would imagine most of the L'Hopital's rule stuff you're probably going to encounter are probably going to come from exactly what we were doing before, which I was like, which is probably going to be for these exponential probability density functions where you have like an x over e to the x, or mostly it's going to be like x to a power over e to the x. Usually in this section anyway, that's where you're going to be using L'Hopital's rule. Well, let's do a few more examples just because it is a tool you should be able to utilize. And I really, really have to stress, you're only allowed to use L'Hopital's rule if you have a 0 over 0 type or an infinity over infinity type. And it can be, so I should say the infinity over infinity, they don't have to be the same type of infinity, meaning one could be a positive infinity and one could be a negative infinity. That's also perfectly fine. So let's look at something like the limit as x goes to infinity of the negative square root of x divided by the natural log of x, which is a negative infinity over infinity type, right? The top is going to negative infinity, the bottom is going to positive infinity. We're still allowed to use L'Hopital's rule because it has to be some type of infinity over some type of infinity. So either plus or minus infinity over plus or minus infinity. So let's use some L'Hopital's rule. That's be the limit as x goes to infinity. Right, the derivative of negative x to the 1/2 is going to be negative 1/2 x to the negative 1/2. And the derivative of the natural log of x is 1 over x. So here's a place where it's easy to get caught in a loop that you don't want to get caught in. I'm going to rewrite this a little bit. So this is equal to the limit as x goes to infinity of negative 1 over 2 times the square root of x divided by 1 over x. And so if we were to plug in infinity here, where is 1 over x going to as x goes to infinity? Oh, darn it. Pen on the finger. Never my favorite. Yeah, totally. 0. Okay. Where is 1 over 2 root x going to as x goes to infinity? Madison with the same answer did, right? I know you didn't type anything, Madison, but yes, it's the same answer. It's also 0. Yeah. So we could mistakenly say, oh, I've got a 0 over 0 type. Let me use L'Hopital's rule again. And not that that would be the wrong thing to do necessarily, but it's not the most right thing to do. So typically after you use L'Hopital's rule, what you really want to do is, if you can, simplify your expression further. And we can definitely simplify this. We can totally simplify this as the limit as x goes to infinity of negative 1 over 2 root x times the reciprocal of this, which is x over 1. And then x divided by the square root of x is the square root of x. So this is equal to the limit as x goes to infinity of negative square root of x over 2. And now it's not an indeterminate form, right? It's not infinity over 0 over 0. It's negative infinity over 2. Infinity divided by 2 is still infinity. So this is negative infinity. Now, here's what that says about this. This tells me that the square root of x gets bigger much faster than natural log of x as we let x go on. And because this fraction is getting infinitely large, that means, or I should say negatively infinitely large, it means the thing on top is much bigger negatively than the thing on the bottom. And that's often what these kind of L'Hopital's rule problems kind of tell us. Like it also, like in a similar way, right? If you're looking at like the limit as x goes to infinity of x to the 5th over e to the x, eventually this is going to be 0, because the derivative of the top is eventually, if you keep taking repeated derivatives, the top is eventually going to be a constant. If you take repeated derivatives, the bottom is still going to be e to the x. So this is going to be 0, which means e to the x is much bigger than x to the 5th, because this fraction is getting small, which means the bottom is the bigger thing and the top is the smaller thing. So let's talk about 0 over 0. Same rules apply, it's just different types of limits. So I don't remember, to be honest, but I feel like we must have at some point in 16a talked about how the limit as x goes to 0 of sine of x over x equal to 1. Maybe they said it was just true. Maybe they showed you a geometric proof of it. Maybe they did something else. It is true. But now with L'Hopital's rule, we can actually say, we can see it another way, right? If we use L'Hopital's rule, we get the limit as x goes to 0 of, well, I should say it, right? This is a 0 over 0 type. Sine of 0 is 0, and the bottom is 0. The derivative of sine of x is cosine of x. The derivative of x is 1. And now if you plug in 0, you just get cosine of 0, which is 1. Well, let's look at an example that might be a little bit more easy to digest. Like the limit as x approaches 2 of x squared plus 3x minus 10 over x squared minus 4, which is totally a 0 over 0 type. If you plug in 0 on top, you get, or sorry, if you plug in 2 on top, you get 4 plus 6 minus 10, which is 0. Plug it on the bottom, 4 minus 4 is 0. So there's a couple ways we could do this, right? We've definitely, there's the old way of doing this would be to factor and cancel. And it's probably the way I would still do most. So oftentimes, so I want to point out, L'Hopital's rule is not always the best rule to use, right? It's definitely a useful tool that's great to use when it works. But sometimes it's kind of a too strong of a tool. Sometimes the old ways are better. So I'm just trying to say is don't use L'Hopital's rule if you don't have to. It's kind of the best advice. So factoring the top, I get x plus 5 times x minus 2. And factoring the bottom, I get x plus 2 times x minus 2. We can cancel the x minus 2s. And then plugging in 2 for the rest, I get 2 plus 5 over 2 plus 2. Great. Or we could use L'Hopital's rule. Using L'Hopital's rule, we get the limit as x goes to 2. Derivative of the top is 2x plus 3. Derivative of the bottom is 2x. So every time you use L'Hopital's rule, you want to think about, can I plug in my limit now? Right? Like, so for this one, we used it and we couldn't really plug it in yet because it was 0 over 0. So then we did some simplifying and it worked out. Or for like this one, right? Like if you do it the first time, and you get 5x to the 4th over e to the x. If you plug in infinity, you still get infinity over infinity. So you do it again. But once you plug it in and you get something that's not indeterminate, then you have to stop. So here, right, plug in 2 and 2, plug in 2, you get 0 over 0. Here you plug in 2, you don't get 0 over 0. So you have to stop, and this is your answer. Plug in 2 and you get 4 plus 3 over 4. Oh, it's the same. Yeah. Let's look at a few more examples, and then we should get back to talking about these special probability density functions. Okay, so let's look at one more. Let's look at the limit if x goes to 0 of 2 to the x minus 1 over 3 to the x minus 1. Interesting. Very interesting. So if you plug in 0, right, you get 1 minus 1 over 1 minus 1, which is a 0 over 0. So we're going to use L'Hopital's rule. Still a limit as x goes to 0. What's the derivative of 2 to the x? It's 2 to the x times something. Oh, sorry. I meant that this problem should be. Is that gonna work out all right? Oh yeah, it's gonna work out fine. Okay. 2 to the x times anybody? Natural log of 2. And the derivative of 3 to the x is 3 to the x times natural log of 3. And then we can plug in 0 and get 2 to the 0 times natural log of 2 over 3 to the 0 times natural log of 3. So we get natural log of 2 over natural log of 3. Interesting. All right, that's probably, I don't know if that's exactly enough about L'Hopital's rule, but we should get back to the other stuff because we've still got a few more things to say. So we had just figured out that the expected value of x, which was the integral from 0 to infinity of x times 1/3 e to the negative 1/3 x dx, was equal to 3. And now I want to talk about the variance. And yeah, the variance is going to be kind of a pain. So what I really want to say is I don't actually want to calculate the variance, because I don't think you're probably ever going to, and it's hard to say. It's very unlikely that anyone's ever going to actually ask you to calculate the variance for this thing the long way. So here's how you find the variance. The variance in general is the integral, and I'm going to use the nicer variance formula. It's the integral from a to b of x squared times your PDF minus your mean squared. Oh, by the way, hopefully you guys saw that I figured out what the problem I was having at the end of class the other day. I was missing a 12. I posted it in Canvas. So if you guys were worried about that problem, there is an answer to it. It's in the discussions in Canvas. So for this one here, right, for this particular one, we would be doing the integral from 0 to infinity of x squared times 1/3 e to the negative 1/3. I keep using x's instead of t's. Sorry, and not a huge deal, but it is good to be consistent. So we want the integral from 0 to infinity of t squared times 1/3 e to the negative 1/3 t minus our mean, which was 3 squared. I suppose we could do this one fairly quickly with a tabular method. So let's do the integral of this tabularly. So my u is going to be t squared, and then the derivative is 2t, and then 2, and then 0. My dv is going to be 1/3 e to the negative 1/3 t. The antiderivative of that is going to be negative e to the negative 1/3 t. The antiderivative of that is going to be positive 3 e to the negative 1/3 t. And the antiderivative of that is going to be negative 9 e to the negative 1/3 t. And my rows kind of got a little bit crooked here. So then we're going to have plus this times this, minus this times this, plus this times this. So here's what we're going to get. We're going to get, and I'm going to try and write it all at once here. It's going to be the limit as b goes to infinity of the integral of this from 0 to b. The integral of this is going to be negative t squared e to the negative 1/3 t minus 2t times 3 e to the negative 1/3 t, so 6t e to the negative 1/3 t, minus 18 e to the negative 1/3 t, from 0 to b, and then minus 9 at the end. Kind of a lot, I know. Okay, I'm going to rewrite this a little bit. So I'm going to rewrite this as the limit as b goes to infinity of negative t squared over e to the 1/3 t minus 6t over e to the 1/3 t minus 18 over e to the negative 1/3, or over e to the 1/3 t. From 0 to b minus 9. Okay, we're almost there, I promise. So then it's the limit as b goes to infinity of plug in the b's. So you get negative b squared over e to the 1/3 b minus 6b over e to the 1/3 b minus 18 over e to the 1/3 b minus, then we plug in 0, you get 0 squared over 1, which is 0, minus 6 times 0 over 1, which is 0, minus 18 over e to the 0, which is 18 over 1, minus 9. Now look what happens. So I don't want to write it all out because we're out of space, but this is going to be 0 by L'Hopital's rule. Right? You take the derivative of the top and the bottom, you get negative 2b over 1/3 e to the 1/3 b. Take the derivative again, you get negative 2 over positive e to the whatever, right? And then you get 2 over something going to infinity. That's going to go to 0. Same deal here. Use L'Hopital's rule once. Derivative of the top is 6. Derivative of the bottom is 1/3 e to the 1/3 b. You get 6 over something going to infinity. That's going to go to 0. This is just 18 over e to the 1/3 b. That's going to go to 0. So we're left with negative 18 minus 9. Okay. And then the standard deviation, of course, is 3. Right? So this is the variance, and then the standard deviation is equal to the square root of the variance, which is just 3. All right. So now here's the big reveal. You don't have to do any of this, unless your teacher says you have to, which I don't think they will. But what I want to say is that here is what we actually get to say about these exponential probability density functions. So for an exponential probability density function, the following is always true. For your probability density function, f of x equal to 1 over a times e to the negative 1 over ax. We can say that, on the interval from 0 to infinity, it is always, always, always true that the mean and the standard deviation are both equal to a. Which also means the variance is a squared. And I'm just going to throw it in there as well, that the median is equal to a times the natural log of 2. That is also true. But the big thing to remember is this. If you have an exponential probability density function on 0 to infinity, which it has to be on 0 to infinity, then you can just automatically read what the mean and standard deviation are. So for example, if my PDF was f of x equal to 1/7 e to the negative 1/7 x on 0 to infinity, without blinking an eye, you could say, okay, the mean is 7, the standard deviation must be 7, the variance is 7 squared, and if you really want to be special, the median is 7 times the natural log of 2. Done. And it's likely that your teacher would expect you to know it this way, and not to like do all the long work, because the long work takes a long time. Or just so this is another example. If my PDF was, say, g of t equal to 8 e to the negative 8x on the interval from 0 to infinity, what's our mean? It's a fraction. What fraction is it? One over 8. And so if there's a 1 over a here, basically whatever the coefficient out here is, your mean is the reciprocal of it. So one more question with this, and then we got time. Then we'll move on to the other two, which are, this is probably the most, the next one's very easy. The last one is more complicated, but it's so much more complicated that we just kind of jumped straight to, here's how it works. So let's say we have this. I'm going to read this instead of writing it. The wait time in minutes at the checkout line at a certain grocery store is exponentially distributed. So exponential distribution of wait time. And we know that the average wait time, the mean, is 2.5 minutes. I want to know what's the probability of waiting less than 2 minutes. So what I need to calculate is I need to calculate the integral from 0 to 2 of whatever my PDF is. But the problem is they didn't tell me the PDF. Well, they gave me enough information to find the PDF. So we know it's exponential, and we know what the mean is, right? And we know if the mean is a, then the PDF is 1 over a times e to the negative 1 over a times your variable. So knowing the mean is 2.5 minutes, I know that my PDF, f of t, is 1 over 2.5 minutes times e to the negative 1 or negative 1 over 2.5 times t. Which you could then maybe write more nicely. 2.5 is 5 halves. So 1 over 2.5 is going to be 1 over 5 halves, which is 2/5. So we can write this as 2/5 e to the negative 2/5 t. So we're using the fact that they told us the mean, and that the mean to figure out what the PDF actually is. So this is going to be the integral from 0 to 2 of 2/5 e to the negative 2/5 t. Okay, and then we would just do the integral, right? So again, the nice thing about this integral without anything extra is it's very easy to anti-differentiate. This is just going to be negative e to the negative 2/5 t from 0 to 2, which is going to be negative e to the negative 2/5 times 2 is negative 4/5 minus e to the 0. So I would write this, sorry, minus negative e to the 0. So I write this as positive 1 minus that. And I don't really care what the number is, but it's approximately 9 even there. All right, so exponential ones, again, you really want to remember this. Whatever number is here, your mean is the reciprocal of that. And your standard deviation is the same as your mean. So if you got something funky like, it's hard to make up, right? If you got something like, if your function was pi e to the negative pi x, your mean would be 1 over pi. Okay, let's talk about the other two. So the next one is super duper not terrible at all. one class had this one and one class had the other one. So the probability that a bus will arrive in a 10-minute interval is uniformly distributed. So that means when someone says something is uniformly distributed, what they mean is that the probability density function is constant. So we have a 10-minute interval. So that means we have the amount of time you wait could be anywhere from 0 to 10. That's our interval. And then the probability, or I should say really the probability density function, is going to be f of t equal to, well, since it's constant, it has to be 1 divided by whatever the length of our interval is. So it looks like this. That's our probability density function. Which makes sense because we know that over your entire interval, the area under the curve has to be 1. And so if the base has a length of 10, the height has to have a height of 1 over 10, so that when you multiply the base times the height, you get 10 times 1 over 10, which is equal to 1. Okay. The nice thing about this one is the things are like super easy to calculate. So like, for example, what's the probability that you wait less than 3 minutes? Well, it's going to be, right? It's going to 3 minutes is 3/10 of the whole length. I mean, it's like, it feels silly to even write an interval here, although we certainly could. It's going to be the integral from 0 to 3 of 1/10 dt. But that's going to be just 1/10 times t from 0 to 3, which is going to be 3/10 minus 0. Essentially, if you know what fraction of the interval you're looking at, that's your answer, right? The interval is 10 minutes long, and we have 3 of those minutes. That's 3/10 of the entire area. What about the expected value? How long do we expect to wait for the bus? So uniform distributions are really kind of very straightforward. So the expected value of t is going to be the integral from 0 to 10 of t times our PDF. Okay, well, that's not terrible. That's going to be the integral of t is t squared over 2 times 1/10 from 0 to 10. Plugging in 10, we're going to get 100 over 2 times 1/10. Minus plugging in 0, we're going to get 0. And let's say that's 50 divided by 10, which is 5. Here's something that's always true for uniform distributions. The average is exactly the middle of the interval. So for a uniform distribution, the average or mean is the same as the median. Right? If we look back at our graph, here's 5. 5 exactly cuts this rectangle in half, so that half the area is here and half the area is there. So for a uniform distribution, the expected value and the mean are the same, and it's exactly the average of your 2 endpoints. So there's a lot. So in fact, there's a lot you could say. So let's talk about the variances for a second. Yeah, variance. So the variance would be the integral of t squared times 1/10 dt from 0 to 10 minus your mean squared. So that's going to give you 10 cubed. Oh, sorry. t cubed over 3 times 1/10 from 0 to 10 minus 25. Plugging in 10, you're going to get 1,000 over 3 times 10. You can cancel 10 and 10 minus 25. So you've got 100 over 3 minus 25 is 100 over 4. I know it seems like a silly way of doing it, but I'm going to factor out 100. So you get 100 times 1/3 minus 1/4, and 4/12 minus 3/12 is 1/12. So you get 100 over 12. And I believe the formulas in general is that for a uniform distribution, so for a uniform PDF on the interval from A to B, well, first of all, the PDF is equal to 1 over B minus A, right? It has to be, so that this length, which is B minus A, times this height, which is 1 over B minus A, multiplies together to get 1. The mean is equal to the average of A and B. And the variance is equal to, I believe it's, I think it's 1/12 times B minus A squared. I should look in the book then, just to be sure. That's certainly what I think it is, but it's always good to check. Let's look real quick. Section 9.3, I believe. Let's see, 9.3. Yeah. Yeah. It's 1/12 B minus A squared, which is exactly what we got, right? We found the variance here. We got 1/12 of 10 minus 0 quantity squared. I don't think you really need to memorize these ones so much. I mean, like, it's kind of impossible not to memorize this one because the mean is just halfway between your endpoints. This one is not super necessary to memorize. You could, but it's not hard to calculate the variance. So for a uniform probability density function, the things aren't hard to calculate because your function is just a constant. All right, got 12 minutes left. Let's talk about the last one. The last one, which we don't do any of the integrating for because we can't. And if you've ever taken any sort of statistics class, you should be familiar with this last one. The standard normal probability density function. So here is the very, very general form of it. The probability density function f of x is equal to 1 over the standard deviation times the square root of 2 pi times e to the negative x minus the mean squared over 2 times the standard deviation, 2 times the variance, really. So this on the interval from -infinity to infinity. So this is your typical Gaussian curve, or more generally known as a bell curve. The bell curve with a mean of mu and a standard deviation of sigma, hence the use of those Greek letters. No one's ever going to ask you to do any calculus with this, really. They're going to give you something and ask you what things are. Let me look back at this homework problem here. Yeah, so like on Ma's homework, he gives you one and then asks you to identify what the standard deviation, the mean, the variance, and the standard deviation are. So let me actually look at this problem I've got here. Oh, where'd you go? Sorry. Oh, that's hilarious. So the problem that's in my notes here is literally exactly the same problem as on Ma's homework. How funny. I don't mind. It's not a big deal. So let's say, fine, I'll change it up a little bit just to make it a little more interesting. Let's say we have f of x equal to, yeah, there's not, it's kind of hard to kind of hide anything here. Let's say f of x is equal to 1 over, I don't know, 9 square root of 2 pi e to the negative x minus 50 squared over 162. Yeah. On the interval from negative infinity to infinity. It's not, I mean, it's reading what everything is not hard. So what's the mean going to be? Well, the mean's going to be 50. It's in the spot where the mean goes. You could try to make this, or someone could try to make this a little bit harder by actually multiplying everything out, but it kind of defeats the purpose of writing it this way. So the mean is definitely 50 here, and the standard deviation is definitely 9, because we can check that, okay, yeah, we have a 9 times, right, the place in the thing in the spot of sigma is 9, and we can double check that 2 times 9 squared is 2 times 81, which is 162. So yeah, our standard deviation is 9, our variance is 81. And there's not a whole lot else to do with this. The only other thing we could say, and yeah, this is really more about statistics. Yeah, so I'll say this because I imagine many of you, probably all of you, will have to take an actual stats class at some point, or maybe already have. But usually stats, there's some sort of stats in everyone's future in the sciences, so that you know how to interpret and read data. Sorry, there's stuff on the floor. Just picking it up. But one of kind of the most useful pieces of information about the normal distribution, or the Gaussian or the bell curve, is that looks like this. The mean is smack dab in the middle. And what we know is that if you go one standard deviation to either side, you get about 68% of all the data. So I know for this distribution here, I could say, okay, what's the probability that x is between, I don't know, 41 and 59? Well, that's exactly one standard deviation to the other side. So I know that's going to be 68% or 0.68. We also know if you go 2 standard deviations to either side, you get about 95% of all the data. So then you could ask some interesting questions like, I don't know, what's the probability for our previous data where the mean was 50 and the standard deviation was 9? What's the probability that we're between, say, I don't know, 41 and 68? Okay, well, let's draw a picture. Here's our mean at 50. One standard deviation, 2 standard deviations. 1, 2. So here's 59, here's 68, here's 41, here's 41 minus 9, which is 32. And we know that between 41 and 59, there's 68% of the data. But this is also symmetric, meaning if you flip it down the middle, the 68% divided by 2 is going to be a 34% here and a 34% here. In the same sort of way, we know that splitting, so from here to here, right, that's 2 standard deviations either side, that's going to be 95% of the data. So that here there's half of 95, which is 47.5%. Same deal here, 47.5%, approximately. So then this little sliver here has 47.5 minus 34, which is going to be 13.5%, as does this. So if I want to find this, the probability being between 41 and 68, I'm going to add 34% to 47.5%. And get that that's going to be approximately 81.5%, or 0.815. Again,